All right, yeah, so today I want to going to talk about the CCP-EM software suite. First, a very, very brief highlights of some new features in the current release, and then some more further discussion on where we're going in the future with new software with CCP-EM. So as you may be aware, CCP-EM version 1.6 was released last week. I was put on the mailing list. There are two main additions. The first is a retooled refinement task. So now RefMac is run with a wrapper of a program called Servalcat by Kitaro and Garab Mushrabov's lab. So there's a ton of new features and functionality with this. I don't really have time to go into it in a matter of time. So just to say, if you're interested in Servalcat and these new refinement tools, it's just recently been published in Acta D. And the second addition to the CCP-EM suite is our new model validation task. So this calculates multiple validation metrics for map and model, both local and global quality metrics, and has a really good feature, which is problem cluster identification. So this is looking at your map and model and finding regions that maybe any independent metric may just find a very small issue with it, but you have a region where multiple metrics are finding different small issues, which suggests that you need to investigate this region more closely. So again, don't have time to go into all the details in this, but if you're interested in the model validation tool, this also was just published in Acta D, and this paper is available. So what I'm really here and really excited to talk about is the next generation of CCP-EM, which is our tool, CCP-EM Pipeliner, and its companion program, Adapio. So what we're intending to do here is really develop a true integrated processing pipeline that can go from raw micrographs coming off the microscope to fully refined, validated atomic model that's ready to deposit in the PDB and EMDB and Empire. So we're accomplishing this through a kind of a suite of curated software, Relion for doing the pre-processing and reconstruction tasks, all the current tools in CCP-EM for doing model building, refinement, and validation. And there's some new tools added for capturing metadata and managing the data that are produced in this workflow. At the same time, we're not trying to be exclusive. So at any point in the pipeline, third-party software can be integrated using a plugin system. So a lot of things that work in a project like this, but the main things I want to talk about today are three goals, which are first, a modern, user-friendly, platform-independent GUI that allows people to access the program easily. Second, robust tools for capturing and managing the data that are generated in your workflow. And scripting tools, which will allow other developers to use our pipeliner as a basis for building more useful applications. So the base layer of the pipeliner is essentially a job runner. It schedules and runs jobs, which are collections of commands that call external programs. It then deals. Oh, okay. It then deals with all the files that are produced, keeping track of everything, managing this pipeline and workflow. And the pipeline is built in a very modular manner, so every job is completely independent. So we have our curated set of jobs that we've kind of approved, but at the same time, any other external program that you can run from the command line, all you need to do is write a job class for it, drop that in the folder, and then that job becomes available in the pipeliner. So the next layer of the pipeliner is the Python API. So this kind of handles kind of larger functions. So for example, the task of running a job may require 20 or more individual tasks to be accomplished. You have to parse the parameter file, figure out what command to run, make a directory to run it in, run the commands, check that they all executed successfully, and on and on and on. And in the API, all of those tasks are bundled into a single function that's called run job. So this gives script people the ability to script the pipeliner and make complicated workflows using Python or through a command line interface with this program called CL Pipeline. And finally, the pipeliner is accessible through a new GUI, which we're working on called Adapio, which I'm going to talk about next. So Adapio is our double duty GUI. Adapio is a double espresso, and the GUI is double duty. It's both a web app and a desktop app. So you can see here, on the left panel, you have a navigation pane. On the right here, I have a project open. I'm editing its basic project information. You can view your entire project workflow as a graph here. So this is the Relion tutorial data processed in the pipeliner. You can see the individual jobs, click on a job to see which other jobs are connected to it. And in the future, we're going to be adding a lot of context-dependent menus on the right click here is to launch pretty much any GUI function from a job in the pipeline. So the actual job list is here. You can see the motion core job is currently running. When you click on a job, the first thing that comes up is this kind of quick results display. So this is individually tailored for each job, and it gives you kind of the at-a-glance results you want to see for that type of job. And this is updated every couple of seconds while the job is running. You have access to the full log files produced by the jobs. Input and output tab gives you access to the actual input and output files used. So for example, here, this is the PDF log file that was produced by this CTF find job. You can open that in the browser or in another window. And then here is the actual star file it produced. Again, you can just open it in another window to inspect it if you are into that kind of thing. So again, every quick results is kind of tailored to that specific job. So here's a class 2D job. It gives you the class averages in a montage. You can mouse over to get information like percentage of the data set and number of particles. For jobs that produce 3D models or maps, there's an integrated 3D viewer. So here's an initial model, and this is opening a binned version of the actual result. So it's optimized to load quickly and be handled well. So here's an example for initial model, and this gives you a really quick check to see how a job is performed. Here is, again, for class 3D, you have your different classes. It's very quick to kind of go in and inspect your individual classes. And again, these are binned versions of the actual data, which are optimized to load quickly and be easy to handle. But if you actually want access to the real output files here, they're available in the input-output tab. Each program has its own kind of suite of things that can be launched. So here you can use Ugly Mole, which gives you a coot-like view. Use that for models. And for maps, we have Mole Star, which again is like Chimera PyMole. And you have access to the full Mole Star functionality here. So you can adjust threshold values, adjust opacity of your map, change colors, record images. You can even download and fit PDBs or molecular dynamics trajectories and actually work with them all right in the GUI. And we're also adding a feature to be able to launch both PyMole or Chimera and Coot directly from the GUI. So if you want to use even more advanced tools, you'll be able to do that. And just one final example here. You see some graphs generated by the polishing job. And all of these objects, graphs, histograms, scatter plots that it produces are all interactive dynamic objects. So you can, zoom and pan and look at them, download actual images to use in presentations and things like that. So when a user creates a job in the pipeliner, you go to the New Job tab, and you'll see there's a list of jobs kind of classified by type. When you open up one of these, the first thing you'll notice is that a lot of the Reliant jobs have been split into individual subjobs. So this is to remove unneeded parameters for any job. So now a job only takes the parameters it's actually going to use. You're not going to have lots of additional values that you may or may not need. Because the list is so big, it's searchable. Here, you can see the class 2D brings up class 2D jobs and the 2D automated selection. Just another example here of the Reliant jobs. Again, the autopick function of Reliant has been split into subjobs for the different types. Pipeliner is aware of what software you have. So here, Krylo is not available, and Topaz picking is not available because the computer I recorded the video on doesn't have those executables. So when you actually run a job, you can see here, click on it, you get an information screen. This gives you information about it, a link to the online documentation, which you can access, again, right in the GUI. And then just say create job. Now you're given a screen to enter all your running parameters. And there's a lot of validation added on here. So the pipeliner is in real time validating everything you enter, giving you file suggestions, and won't let you run a job that's going to immediately fail. It'll instead raise a warning and tell you why and let you correct your errors. So as you may imagine, when we have a full integrated pipeline going from start to finish, we're going to have a massive number of jobs and subjobs. And it's going to be really a lot to handle, having to sort through all of these to figure out exactly what tasks you want to run. And so the solution that we've built for this is a skin system. So all you have to do is edit a configuration file in the GUI, and you can build a specific skin. So here is the rely-on single particle skin. So now if you go to the jobs list here, you will see that you have only the rely-on jobs, and they're in the kind of sequential order that you expect from the rely-on GUI. So again, if we go here to the class 2D section and expand it, you'll see that the only class 2D jobs you have are expectation maximization, single particle 2D classification, and VDAM classification. So here's another example of a skin. This is a rely-on helical reconstruction skin. So again, when you go to the jobs section, you have the jobs in the kind of sequential rely-on order that you're used to. And if you look at here, you only have the helical versions of these jobs. So if you click on here, you see, for example, 3D classification for helical objects has a whole bunch of parameters that are not needed for this single particle. So these are only included in the helical job. At the same time, we don't want to ever limit our users as to what programs they can use. So you can always tell it to show all the jobs, not just the jobs in your current theme. So now you can see all the single particle versions of these jobs are back. And at the top, the non-reliant jobs are back. So for example, model building using Buccaneer, and anisotropic map analysis using cryo-EF are now available again. So there's lots of kind of ideas of how we want to use this skin system. So a facilities manager could decide, and you have a specific set of supported software at your facility. So you have a skin that only gives access to those pieces of software. If you're going to teach beginners or run tutorials, you could again have a skin that has just the software they need, all in sequential order, ready to go. And if you have a project where you have a really defined workflow, you could actually make a skin for just that project, having again all the jobs you need in sequential order and no extra stuff to worry about. So the second really big issue we're talking about with this pipeliner is how to manage all the data this giant pipeline is producing. So you've solved a structure and published. You hopefully wrote a very descriptive processing methods section. You hopefully put in a workflow diagram to describe kind of your work. You have a table 1 through X that has all your processing information and collection data statistics, all of that. You've been good and you've uploaded it to EMDB and PDB and Empire. You've filled out all of these forms, which I think a lot of us have suffered through. But the question is, even with all this, could you actually reproduce this workflow with complete fidelity? And the answer is no. I mean, you're never going to know every single parameter used in every single job without actually seeing the actual data processing. And we say, as machine learning, especially, is becoming more and more prominent in cryo-EM, all these published methods and the data in the various databases are going to become really important as for building training sets. And we all have an interest in these being as complete and as accurate as possible. So the pipeliner is, again, setting up with all these metadata tools to help us kind of root out the inaccuracies and incompleteness that we're seeing in these depositions. So you have basically things like transcription errors, just copying things, not knowing where to find specific pieces of data in your big complicated workflow, and simply the fact that there's not enough space in a paper to literally put down every single parameter you've used in your processing. So because the pipeliner has a network map of the project, you're able to trace individual jobs. So for example, here is some processing in rely-on, starting with raw data and ending with 3 different post-processed sharpened maps. If we take a specific map, let's say 21, we can generate a critical path which shows just that terminal job and all of the jobs that contributed data to it. So now we can work in and use the various tools in the pipeliner to really audit the entire workflow process for this job. So first, every job records a complete history of every operation that's ever been performed on it. So here's, for example, an import job. You can see that it was run, it was continued multiple times, it was cleaned up at one point, and it was used to create an archive. And then again, every single command that was run has been saved. Second, in the modular nature of the pipeline, every job defines what kind of metadata it collects about itself. So here's a 2D job, a class 2D. Again, first, all of the job parameters are automatically added to the metadata file. And then the job has a specific set of metadata it returns. So in this case, it returns the number of classes, the number of non-empty classes, a class distribution, which you could use to make a histogram, resolution of all the classes, particle count, number of contributing micrographs, and the actual defocus range found in your classes. Not the nominal defocus, but the ones of the actual particles. So since we have this every job returning its own metadata and we have a critical path for your terminal job, You can ask the pipeliner to create you a metadata report for an entire project or from any job upstream or downstream. So again, here, we've generated it for the motion core job. It knows it has one parent, which is the import job, and it returns the entire metadata feed for all of those jobs. You'll also notice here, if you can see it, that the import job was actually continued. So this is the original run of it, and then the second run of it. So this is it was a limitation in the original Reliance setup, is that if a job was continued or overwritten, it didn't necessarily know that it happened. But here, the pipeliner is tracking everything. So all of these files that I'm showing are in JSON format, which is really universal. And they're a schema published with the pipeliner. So it's to be straightforward for anyone to write their own scripts, to scrape that out of these files, use it for your own purposes, such as automatically generating tables or method sections or anything like that. And for our industrial users, I think this JSON format will make it really easy to integrate this into an existing LIMS system. And finally, we are currently developing tools for aiding in deposition. So the one that's currently implemented is for empire deposition. You pick a terminal job, you ask it for an empire deposition. It then figures out what type of deposition you might be able to make from that. So you can deposit any or all of these things from a final map. So raw micrographs, corrected micrographs, the particles, or the polished motion corrected particles. It creates an upload directory, puts all the files you need to upload into that directory, makes sure all the naming conventions fit and work and everything is set up. And then it spits out a file that you can, is indexed to the schema of the specific database you're working. So all of the pieces of information that the pipeliner has are now available in the format that the database uses. And we're going to hopefully work very closely with the administrators of these databases to find ways to use these files to aid in doing uploads. So for example, you might be able to eventually upload this file with your deposition. When you start one dep, a big percentage of your fields are automatically filled with the data the pipeliner has scraped, you know is accurate. Right. We also have tools for data management. I think facility managers will be very happy about this. The first, familiar to most users of Rely on, is the cleanup function. It deletes non-essential files and intermediate files, temp files, things like that. Again, in this modular nature, every job defines what it considers a non-essential file, but at the same time, the pipeliner is aware of its project network, and it'll never delete files that are important for other jobs, even if a job asks it to. So here's an example of beta-gal processed with the pipeliner, a very small data set, and it's binned. Took 20 jobs, it produced 5.2 gigs of data. If we run the cleanup, we cut that project size down to 2.7 gigs, almost cut in half. The second data management tool is this archiving tool. So there are two types of archives. The first archive is a full archive, where this just takes the terminal job and all of its parent jobs, bundles all of the directories that they were done in into a single archive, packages them up neatly. So this is complete, exact preservation of your entire workflow and all your data. And the second is the simple archive, which rebuilds the directory structure, puts in the parameter files, and then gives you a script which allows you to run the entire project from start to finish. So all you need to do is give it the raw data and press go. So obviously there are a bunch of stochastic elements in processing. So this isn't a way to have exact high fidelity recapitulation of your results, but instead it just allows you to preserve your workflow. And it also has an alternate use where if you have a project, let's say, solving the same protein over and over again with different ligands, where your workflow is very, very similar, it might be possible to use a simple archive script with a new data set that uses the exact same processing setup, as long as all of your choosing of classes and steps are automated. So here, again, this entire project, the full archive is only 13 megabytes, and the simple archive is 350K, and it's a single file, set of files. All right, so the final thing we have here is we really want this pipeliner to be a tool for developers to use for scripting. So here is a bash shell script that is a pre-processing pipeline. Again, starting a project, scheduling and import motion core and CTF find jobs, running that schedule, and then creating a metadata report. Here's the same script, this time in Python. Again, start the project, schedule the jobs, and run the schedule. And I'm going to highlight now 3 tools that have been built on top of the pipeliner to kind of show you what kind of things people can do. So the first is a re-implementation of the Rely on It scripts. This is by Dan Hatton at Diamond Light Source. So this is a full on-the-fly pre-processing and data evaluation suite doing batched processing of micrographs. It runs all the pre-processing. It runs their icebreaker scripts, our programs for ice quality analysis, picks using either Krylo or Relion, and then works all the way through 2D classification, generation of an initial model, and even class 3D. So this allows you a really quick kind of on-the-fly evaluation of your data set. So Relion has its own GUI, which Diamond users can just launch, but this is using, you can see here, there are very few actual parameters for all the work that's being done. So this is really quick, straightforward. But this, on its back end, is running the CCP-EM pipeliner to do all the work. And then this speaks to their data evaluation system, which allows you to, on the fly, watch as your data set is collected, generate 2D and 3D classes. Another tool that I've included as an example of scripting the pipeliner is a benchmarker. So here you give it a parameter file or a series of parameter files where one or more of the parameters is a list of values rather than a single value. And it just runs all the possible combinations of those variable commands, reports the time for each step and the total time for each processing. And this is set up to run in parallel, so you're limited only by how much computational time you have. And in theory, you can run as many computations as you want, and it'll only take as long as the longest job, as long as you have enough room on your cluster to do it. And the final tool I have is this called subset reconstruction. So this, you hand it a Relion refinement job. It takes the refinement particle set, splits it into the 2 half sets, shrinks each half set, recombines them, and then does the refinement again using the existing alignments, and then just repeats this process over and over, iteratively shrinking your data set. What this ends up giving you is the exact same map, just with a decreasing signal to noise. This was originally actually written for one of my colleagues at CCP-EM who just needed this specific type of data set for a project, but I've now expanded it into a function similar to the original B-factor scripts in Relion. So these scripts did the same thing where they just did a reconstruction over and over again with a decreasing number of particles and used it to estimate how much resolution you may gain by adding additional particles. So this works in the same way, looking at the B-factor that was fit to each of these maps and makes a prediction. So subset reconstruction is a bit more conservative than the B-factor script in what it estimates you can gain, but it has the same function. Okay, so I haven't had a chance to talk about all the features. There's a lot in here. But in the near future, I think what we're looking here is full implementation of all of the jobs in CCP-EM. So as you can see, this is very Relion-centric. I'm starting at the beginning and working my way through. So next will be implementation of the model building, refinement, and validation tasks. We already have a tomography pipeline in the works. So we'll eventually have full support for tomography and sum-tomogram averaging within the pipeliner. Tools for deposition for EMDB and PDB, and additional functionality and cosmetic improvements on the GUI. So please participate. The pipeliner is fully open source. You can see the source code at GitLab. The documentation is very extensive and available online. And for developers, there's a guide to writing plugins available. I'm happy to help you write a plugin for your specific piece of software so we can integrate it into the pipeliner ecosystem. And remember, if you write a plugin for the pipeliner, you get a nice fancy GUI for free. Yeah, and if anyone's interested in seeing Catch Me During a Break, I'm happy to give you some live demos of how it works. Yeah, so thanks to everyone who works on this project, everyone in the CCP-EM core team, CCP4 and STFC, all the developers who contribute the software which goes into the pipeliner. The two main stakeholders of this project who really drive it are Georges Shears and Gerard Bercon. And all of this work is funded through CCP-EM by UK Iran Wellcome Trust. They're funding CCP-EM and support from Global Phasing and all of our commercial license holders whose commercial license fees are also supporting this project. So thanks, and with that, I'm happy to answer any questions.